מקליט?
מוקלט.
נהדר. אהלן אור.
היי ליאור, ברכות.
תודה. אני מקווה שעכשיו תצליח להבין על מה חפרתי לך עם המרחב הזה.
כן, גם אני מקווה.
לפחות את המוטיבציה.
Okay, I think we can start. ליאור, אתה רואה מישהו חסר? מישהו זה VIP חסר?
לא ראיתי.
אוקיי, אז בואו נתחיל. אוקיי, so let's start. First of all, congratulations to Lior for completing his PhD. When you see the title, Universal Limit of Nodal Statistics, Rami, do you want to say a few words?
Yes, just a few words.
Okay.
So I'm happy to be present in this PhD seminar. Lior had many results and wrote a very nice thesis, which I recommend all of you to read. However, since he wants us all to learn and understand, he will concentrate in this talk on a particular topic of the thesis. And in order not to waste more of his time, Lior.
Okay. And waste 10 more seconds of your time. During the talk, Lior won't be able to pay attention to the chat. I won't do that, but I think you can also interrupt him with questions as you go. So I'm been looking at the chat if you want to ask then, and then I interrupt Lior, or you can just do it yourself. Lior, the stage is yours.
Thank you, Neil, for letting me do my talk in this PD and analysis seminar. And thank you all for coming. And I will take advantage of this point to thank also Rami for being such a great advisor. And this talk, as Rami said, is just one part of several projects that I did during my PhD. This part is joint, of course, with Rami, my advisor, but also with a collaborator named Gregory Berkolaiko. And what I'm going to talk about is quantum graphs and the nodal statistics of quantum graphs, and a special conjecture about the universal limit for the nodal statistics of quantum graphs. So let me start. This is the outline of the talk, and I will start from a brief introduction, motivation from the point of view of Sturm theory. So just as a reminder, If we're looking at the solutions of this eigenvalue problem on the interval that satisfy Neumann conditions, so the derivatives on the start and the end are 0, then the solutions look like that. It's very easy to solve, but you can see that if I give you some solution, I tell you that's a solution, but I don't tell you which one is it if I order them according to their eigenvalues. So one can just observe that each one of them, the position of each one in the spectrum, is exactly as the number of points where this line intersects 0. So I can just count the point and tell you which one is it. This is the famous Sturm result about nodal count. So if I said that the nodal count is the number of points in the interval for which f is 0, then Sturm showed that the nodal count phi n is equal to n. And it's general for any Sturm-Liouville operator, not just the Laplacian. Now we'll stick with the Laplacian, but go to more general domains, not just the interval. So if I take several intervals and I glue them together in form of a graph, so this is a metric graph, which we call a quantum graph. I will define everything later rigorously. I now just give a brief motivation. So if we have such a metric graph, we can talk about the eigenfunctions of the Laplacian on the metric graph. We can order them according to their eigenvalues and count the number of nodal points. And you can see here the 3rd, 6th, and 10th eigenfunctions and their nodal count. And suddenly you can see that although phi 6 is equal to 6, phi 3 is not equal to 3, phi 10 is not equal to 10. We have some kind of a small deviation. What we will show in a few slides, we will show that this deviation is actually bounded. And a conjecture raised by Gnutzman, Smilansky, and Weber in 2003 in their first work on nodal count of quantum graphs, they raised the following conjecture. So for well-connected graph with incommensurate bond length, I will talk about it later. What does it mean? The distribution of the number of nodal domains in the interval mentioned above. So this you can think about it as phi n in the interval where I have going from n to some kind of deviation. The distribution, the distribution of this deviation converges to a Gaussian distribution in the limit when the number of vertices is large. So here they count the number of nodal domains and not the number of nodal points, but that's irrelevant to our story. It's for almost all eigenfunctions, it's just a shift. So it's the same statistics. Now let me provide some numerics that support this conjecture. So for example, if I take complete graphs, these are well-connected graphs, I take the complete graphs of 4 to 15. For example, this picture is the complete graph with 10 vertices. Each vertex connects to all other. And here you can see their distributions, the distribution of the values of phi n minus n. As I said, there are only a finite amount of numbers that we can get. And we can look at some kind of a normalized histogram of the first median eigenfunctions that I show here. And you can see that as the graphs go bigger and bigger, these distributions become more and more Gaussian-like, which support this conjecture. Now, this conjecture didn't come from thin air. It actually followed by a conjecture about nodal statistics that regards planar domains. I would not get into it. I would just say that there is some part here that Blum, Gnutzman, and Smilansky were able to prove some kind of a universal distribution for integrable domains. But for the majority of the domains, in particular the chaotic domains, we don't have any analytic result. There's only a conjecture about some kind of behavior that is concentrated around some point, and the concentration is Gaussian-like. And a proof for something similar was done by Nazarov and Sorin for random eigenfunctions on a sphere, showing some result about the concentration of the number of nodal points for a random eigenfunction on a sphere. So that's the motivation from manifolds. Now let's get back to graphs and define what's a quantum graph. So I'll start with a graph. I will also call it a combinatorial graph so it's clear that it's not a metric graph. And a combinatorial graph has vertices, edges. We denote the number of edges by capital E. The graph is not necessarily simple. We can have multiple edges, and we can also have loops. When I say a cycle, I mean a closed simple path. When I say a loop, I mean an edge connecting a vertex to itself. For example, in this graph, you can see two loops. As I said, a metric graph. So we have a bunch of edges. Each edge is a segment of some length, and we glue them together according to the discrete graph structure. And I will denote it by gamma with subletter L, where L is the vector of edge length. So given such a metric graph, we can talk about the functions, as I showed you before, on this metric graph, and we can also talk about the Laplacian. So the Laplacian would go from the Sobolev space, from the right Sobolev space to the right L2 space, where this Sobolev space and L2 spaces are simply the sum of the spaces on every segment. And the Laplacian acts edgewise, meaning on every edge, and the restriction to every edge is just minus a second derivative. In general, it's not self-adjoint. In order to become self-adjoint, I need certain vertex conditions, the analog to boundary condition. So the vertex condition would be continuity on the vertices and sum of incoming derivatives, which equal to 0. This is called usually Neumann, standard, or Kirchhoff vertex condition. And now, as a terminology, when I say a standard quantum graph throughout this talk, I mean the following. I mean a metric graph, which is finite and connected, equipped with the Laplace operator, with bounded to the domain of Neumann vertex conditions, functions that satisfy Neumann vertex conditions. And also, I will always assume that the graph has more than one edge. It's not trivial. We have no vertices of degree 2 because these are singularities that we can remove. And now, what was called in the conjecture, yeah?
אני רק רציתי לבקש, ניר, אתה יכול אולי לעשות מיוט לכל המשתתפים?
עשיתי, חוץ מזה מישהו שהוא עקשן פה, EN, מישהו EN שיקבל את עצמו, כי איכשהו אני לא מצליח להשתמש עליו.
אוקיי, אני ממשיך בינתיים. אז אני מניח שאין ורטקסים מדגרי 2, and we also assume that the edge lengths are rationally independent. So what I mean by rationally independent, that's the incommensurate bond length that were talked earlier. It means that they are independent over the field Q. If I sum them with any rational coefficients which are non-zero, it doesn't vanish. This would be, you can, for now, you can just forget about it. It will become relevant when we get to the methods and to ergodicity. This is where it's going to play a role. Sorry. So given such a standard graph, it has the following properties. The Laplacian is self-adjoint. We have a discrete spectrum. The first eigenvalue, which I call the zero eigenvalue, is always zero, corresponding to the constant eigenfunction, and it is simple. And all other eigenvalues are arranged in increasing order, including multiplicity, goes up to infinity, and we can assign them an orthonormal basis of real eigenfunctions, the Fn. Now it will be convenient, instead of talking about the lambda n, to talk about their square root, Kn. So whenever I would talk about eigenvalue, I will usually talk about Kn. Now we can define the nodal count. So given such a function, we can denote its nodal count by simply the number of points along the graph where the function vanishes. But in order for that to be well defined, I need two things. I need first that the eigenvalue is simple, so n is well defined. And the second thing, I want the vertices, I want the function not to vanish on the vertices, because then I don't know how to count it and it causes problems. And I would call a function that satisfies these two properties, I would call it generic, and I put generic on those marks because it is not always the case. So a possible pathology can be loop eigenfunctions, that is eigenfunctions supported on a single loop. It can only happen if I have loop, but whenever I have loop, I do have eigenfunctions supported on this loop. Now, not only that I have eigenfunctions that are supported on the loop, I have infinitely many eigenfunctions supported on every loop. So that's not something that I can just neglect, and I will have to deal with it some way. And this way is the following. So our tool to quantify sets in the spectrum or quantify integer sets is the following. We say that an integer set has density if the following limit exists. This is what enables us to say statements like half of the integers are odd and half of the integers are even, using such a density. Now, a theorem due to Berkolaiko and Lior from 15, which we in our paper generalized, says the following. So given a standard graph, we denote the two index sets, the indices for which Fn is generic and the indices for which Fn supported on some loop. And we're saying that the two index sets have densities, and not only that they have densities, we can say even exactly what are those densities. The density of the loop eigenfunctions is half the total length of loops divided by the total length of the graph. So it's something that is always less or equal than half. And the density of G is 1 minus that, meaning that the two sets, these two sets together have density 1. So almost every eigenfunction is either generic or a loop eigenfunction. In specific, if we don't have loop, almost every eigenfunction is generic. So we can state the same thing just in different words, saying, as I said, almost every non-loop eigenfunction is generic. Therefore, it has well-defined nodal count. And now we can talk about the nodal count. So recall, whenever n is in G, I can define phi n to be the number of points where Fn vanish. And as Glucksmann, Smilansky, and Weber showed, there is an upper bound to phi n, and whoever know the famous courant bound for planar domains and manifolds, so their upper bound is exactly the courant bound. The lower bound, which is something that we don't have on manifolds, was first given on trees in these two papers, and in 2007, Berkolaiko generalized it to any graph, which means that now for any graph, for any standard graph, for any generic function, the phi n is between n and n plus beta, where beta is the first Betty number of the graph. So that's the number of cycles of the graph. That's E, number of edges minus vertices plus 1. this number would play an important role in our work. Now, it is only natural to define the nodal surplus. This is exactly the deviation that we were looking after, the deviation of phi n from n. And as the theorem says, this deviation is bounded between 0 and beta. So it has a finite number of possible values. And we can define the nodal statistics as the proportion out of all generic eigenfunctions, the proportion of those that get a certain nodal surplus. So I take all the integers that are generic and are below some capital N. I'm looking at how many out of them have sigma n equal to j, have nodal surplus equal to j, and I take the limit. And if these limits exist, and that's a big if, then the nodal statistics is well defined. So what I want to show is that these sets has density. Now, in such case, we can talk about the nodal statistics as a random variable. So we can talk about sigma as a random variable that has distribution according to these limits. And given this terminology, we can now restate, reformulate the conjecture of Gnussman, Smilansky, and Weber as follows. So the nodal surplus distribution of a standard quantum graph gamma L with first Betty number beta approaches a Gaussian distribution centered at beta over 2 in the limit of beta goes to infinity. Namely, if we normalize it correctly, this would converge to the standard distribution n 0, 1, where the convergence above is in distribution, and the variance that we're talking about is of order beta. So this is our one of our goals, and I will refer to this as the universality conjecture. And now let me talk about our main results. So our first result is well-posedness, which means that these integer sets have density. And once they have densities, then the nodal distribution is well-defined. So we can talk about the nodal distribution, P of sigma equal to J, as the density of this set divided by the density of G. That's exactly the limit that I showed you earlier. Moreover, we were able to say that this distribution is always symmetric on the interval 0 to beta, meaning that 0 and beta, or 1 and beta minus 1 would have the same probability. Now, as an immediate corollary, if we have a standard graph, then the average nodal surplus, because of this symmetry, is beta over 2, which means that we get an inverse result. Just by knowing the nodal surplus and taking the average of the nodal surplus, I can get the first Betty number of the graph. So the first Betty number of the graph is the topological characterization of a graph, and I get it immediately by just looking at the average over the nodal surplus. So that's a nice application. Now, the next, before I'm going to the next, let me show some examples. So just some examples for a graph with low beta. So here are the distribution for this graph, and for this graph. This has beta equal to 2, beta equal to 3, beta equal to 3. And you can see here their distributions. What I want you to notice is that these two have beta equal to 3, but have different distributions. This one doesn't have any values 0 or 3. This one does have values 0 and 3. All have the symmetries the symmetry at the middle that we talked about. Now let us look at examples for some larger graphs. So here are just some graphs, the Z2 mod 6 Z2, just this lattice when we glue this side to this side and this side to this side. And here I just sampled a random graph from using the Erdos-Renyi random graphs until I got a graph which was connected, and then I calculated it. And here I just took the 10 complete graph that I showed you earlier. And you can see that if we squint our eyes a bit, it looks exactly the same. They're nodal distributions. And that's exactly what the universality conjecture is telling us, that we expect to see the same distribution as we go to bigger and bigger graphs, not like in this case. So now we have been able to establish the universality for a certain families of graphs. So let me describe those families of graphs, and I call them trees of cycles. So what do I mean by a tree of cycle? I mean that every two cycles, here in order to emphasize the cycle, I color their interior with a color. So every two cycles can be separated by an edge. For example, these two, I can remove this edge and then they are disconnected. These two, I can remove an edge and then they are disconnected. So whenever I have such a graph, I call it a tree of cycles. And the theorem that we were able to show is that given a standard quantum graph, which is a tree of cycle with first Betty number beta, its nodal distribution is binomial with beta and half. Namely, the probability to get sigma equal to j is beta choose j 2 to the minus beta. Now, a very, very important remark here is that in general, this distribution depends on the choice of metric, depends on the graph structure, not only on the graph's metrics, on the edge length, not only on the graph structure. But as we show in this case, if we're looking at tree of cycles, we don't care about the edge length, we just need the edge length to be rationally independent. Now, as an immediate corollary of this theorem, here is an example where you can see this binomial. As an immediate corollary, we established the universality conjecture for this family, because central limit theorem tells us that binomial converge to Gaussian, exactly in this way. So if we have standard quantum graphs, which are tree of cycles, then they satisfy the universality conjecture, and this...
מהמחזור, שכרגע עושה את הפרזנטציה דוקטורט שלו. אז הוא שלח קישור לחבר'ה מהמחזור.
So this is the corollary of this theorem, is that we were able to establish the universality, including the order of the variance for these trees. So now let me get into the method and proofs. Nir, how much time do I have? Nir?
25.
Okay. How much time do I have?
25.
Thank you. Okay, so now let me talk about the method and proofs. So the main tool that I'm going to present here is the secular manifold. So what is a secular manifold? Given a graph, a discrete graph, we can put all kinds of edge length on it, and we can take all kinds of positive number k's, and we can ask whether k squared is an eigenvalue of gamma L. Now, this spectral question can be asked equivalently whether the eigenspace, the following eigenspace is non-trivial. What is this eigenspace? This is the vector space of all functions on gamma L, which satisfy Neumann vertex conditions, and our eigenfunctions of the Laplacian with eigenvalue k squared. I will use this notation. When I say the eigenspace is not trivial, meaning that its dimension is not zero. And the next argument will show why it is enough to ask only about those edge lengths which are where every entry is between 0 and 2 pi, and that the eigenvalue, I don't care about any k square, I can just look at the eigenvalue 1 and ask when I have L in this regime such that gamma L has eigenvalue 1. So what's the argument? Let f be such a function in this eigenspace. Then on every edge, its restriction to the edge is of this form. It's just a sum of cosine and sine, where they have inside k times xe. Xe is my coordinate. When I take second derivative, I get minus k squared outside, and it satisfies the eigenvalue problem. Now, the first thing I can do is just rescale the graph. So instead of having x going from 0 to LE, I have x going from 0 to KLE. Now the new graph has edge lengths that are equal to KL, and I have a new eigenfunction, which I just define exactly the same. And now I have this, now inside I don't have k, I just have x. So when I take the second derivative, the eigenvalue is 1. So using such a scaling, I can get from any eigenvalue to eigenvalue 1. Now, if I have an eigenfunction of eigenvalue 1, then it is 2 pi periodic on every edge, which means that I can extend every edge periodically, extend every edge with segments of 2 pi times an integer, as you can see here in this picture. So I'm starting with some function on a graph, and then I just shove in at the middle a 2 pi segment, or I shove in the middle two 2 pi segments, 2 periods. And I can do that, and you can see that it doesn't change the values of the function on the vertices, nor their derivatives. So I still get an eigenfunction, and it's still an eigenfunction of eigenvalue 1, only on a different graph. So let me get this argument as follows. So using the following notations, the curly bracket would mean modulo 2 pi. And when I take RE and take modulo 2 pi, I get this e-dimensional flat torus. And now whenever I have this point, this kappa, which is the bracket of KL, I can talk about the corresponding graph, which has edge lengths, which are according to kappa, and I take them each one between 0 to 2 pi. So these are exactly the edge lengths that lie in between 0 to 2 pi. And using both scaling and extensions, I can get to the following isomorphism between eigenspaces, which gives me that the eigenspace of gamma L with eigenvalue k squared is isomorphic to the eigenspace gamma kappa with eigenvalue 1. So whenever I want to know if this eigenvalue is non-trivial, it's enough to ask whether this eigenspace is non-trivial. And an important part that I'm going to discuss later is that this isomorphism that I just showed you preserves the vertex values of the eigenfunctions. So now what are we going to do with that? Let us define the secular manifold. So the secular manifold is going to be exactly those kappas such that 1 is an eigenvalue of gamma kappa. Namely, the kappa in TE such that the dimension of the eigenspace is larger or equal than 1. And as an immediate lemma, if k is a positive number, and it's an eigenvalue of gamma L, if and only if its curly brackets of KL lies in sigma. So let me just show you some pictures. For example, if I take this star graph, this in orange, you can see it's a secular manifold. It has 3 edges, so I plot it in the 3-dimensional flat torus. So you should think about the faces of the cubes as they are glued together periodically. And you can immediately see here that it's not a manifold, as they call it. It's actually a variety. And as we can prove, it's a real analytic variety. It's the zero set of a real analytic function, but I don't want to get into it. And you can see here I plot some kind of a line. This line is going in the direction of L, where K is my parameter of how much I'm going in the direction of L. It goes from 0 to infinity, And whenever this black line, this flow, hits the secular manifold, I get a k, which is an eigenvalue. Meaning, this point would be k1L, this point would be k2L, this would be k3L, this would be k4 times L, etc., etc. This is how we can get the eigenvalues from the secular equation, from the secular manifold, and these are the eigenvalues for any choice of edge length. I can get the eigenvalues in such a way. Now, the next thing that I want to talk about, using this isomorphism, I can say something more than just whether one is an eigenvalue or not. I can say whether one is a simple eigenvalue, namely whether the eigenspace contains only one eigenfunction. So we define the set for which kappa has one as a simple eigenvalue as the regular part of the secular manifold, and that's exactly whenever the dimension is equal to 1. Whenever we have such a kappa, where 1 is a simple eigenvalue, we can look at the only eigenfunction that lies inside this eigenspace. It's only, of course, up to scaling by a factor, up to a multiplicative factor, so we can just take it to be normalized and real. And we will call it the canonical eigenfunction. This would be f kappa. So, for example, if this is the secular manifold, and I take this point at the middle, then I would get this graph. The point at the middle would give me what are the edge lengths of the graph, and on this graph I have exactly one canonical eigenfunction. Another example, I take this one. Now you can see that this one lies in a regime which is where the entries are smaller, so we have smaller edge length, and this is our eigenfunction. Now let me just check your intuition. What do you think would happen if I take this point and just move it just to the layer above, just 1 pi above? What do you think would happen? Anyone has a guess? So I would simply add another piece of pi. So that's the same eigenfunction. I just added another piece of pi, and that's why I have this, whenever I have such a loose end, I can always add a pi. So my secular manifold would always be invariant to shift by pi in this direction. So that's just for some intuition about what this secular manifold is all about. Now, the next definition that I want to talk about is the set where kappa, all those kappa for which f kappa is generic. So when kappa lies in sigma reg, the 1 is a simple eigenvalue, so f kappa is generic if f kappa doesn't vanish on vertices. For example, let's consider this graph, which has 2 edges, one loop and one which is not a loop. So the secular manifold is embedded in the 2-dimensional torus. And you can see here the secular manifold, and I can partition it to the following parts. So the blue parts are the generic parts. Whenever I get a point here, this eigenfunction is generic. These parts, these orange parts, are non-generic, and those black points where I have 2 parts that meets are the singular points. These are the points that doesn't lie in sigma reg. These are the points in which 1 is an eigenvalue, but not a simple eigenvalue. Now, to wrap everything that I said up to now to some kind of a lemma, if I have a standard graph, gamma L, with some choice of L, and I have K, and I let K be my time on this flow, on this black flow. You can see this black flow going. And I'm taking kappa to be the curly brackets of KL. Then K squared is an eigenvalue of gamma L if and only if kappa lies in sigma. And it is a simple eigenvalue if and only if kappa lies in sigma reg. and it is a simple eigenvalue with a generic eigenfunction. So the eigenfunction of K on gamma L is generic if and only if the canonical function, eigenfunction of kappa is, that's a mistake, that's supposed to be sigma G. Lies in sigma G, it means that the canonical eigenfunction is generic. So at this point, let's think what happens if we choose the edge length to be rationally independent. So in this example of having two edges, being rationally independent means that the slope here is irrational. And what we all know is that in case that this slope here is rational and I let this line to go to infinity, this line is going to cover the torus densely. It's going to wrap around the torus densely, getting to almost every point. And therefore, it's going to hit this manifold in a dense set in almost every point along this manifold. And not only that it's going to be dense, it's going to be equidistributed according to some measure. This method was first introduced by Brian Gaspard in 2000, where they introduced this following measure. So we call it the Brian-Gaspard measure. And this is the measure that I'm taking on this manifold. N is the normal to sigma, ds is the Euclidean surface element. Essentially, what is this measure? Locally, if I take a small enough set, locally this measure is exactly the up to normalization, it's the cross section of this set. So I take this set and I'm looking, if I'm looking at this set in the direction of the flow, of my flow, it has a certain area of the cross section, and this is its measure up to a global normalization that I want the total measure to be 1. So now that we have the Brian-Gaspard measure, we can talk about the ergodicity. So what the ergodicity statement says, and it was first proved by Brian-Gaspard in 2000, then Berkolaiko and Wien gave a more rigorous proof in 2010, and Colin Deverdier in 2015 gave another rigorous proof. And it goes as follows. So if gamma L is a standard quantum graph, remember, we assume that the L's are rationally independent, then this sequence of points, the K and L points, which we know are going to lie on the secular manifold, are equidistributed on the secular manifold according to the Brian-Gaspard measure. So instead of going to explain what I mean by equidistributed, it means the following. An equivalent statement is the following. If A is a Borel set in sigma that has boundary of measure 0, then this integer set, that's all integers for which K and L lies in A, has density. And this density is exactly the Brian-Gaspard measure. So it means that if I want to know how many points are hitting A on average, it's going to be exactly according to its cross-section, according to the Brian-Gaspard measure. This is I think the main tool when we are trying to prove things about statistical behavior of eigenfunctions on quantum graphs. So the next thing that I want to talk about is the following lemma. The following lemma talks about the inversion. So you can see that this manifold has the following symmetry. If I take a point and I take minus of this point, okay, so that's minus but modulo 2 pi, so here it's going to here, then this is an isometry of sigma that preserves the Brian-Gaspard measure for any choice of L. So just to, not a proof, but a hand-waving argument, you can see that if I take such a set and I do apply the inversion, the cross-section doesn't change because L, the direction of L under the inversion goes to minus L, so we get the same cross-section. So now we have the machinery, the needed machinery in order to sketch the proof of the well-posedness. So given a generic Fn, we want to relate its nodal surplus to the nodal surplus of the canonical eigenfunction. How do we do that? We define sigma, a function from sigma g to 0 up to beta, as the nodal surplus of the canonical eigenfunction. So it would be the nodal count, the number of zeros of the canonical eigenfunction, minus its spectral position. What do I mean by its spectral position? So I want to know where one stands in the spectrum of gamma kappa. So what does it mean? It means how many k's up to 1 are eigenvalues of gamma k, of gamma kappa. And this minus this is the nodal surplus of f kappa. And now we have a lemma that says that whenever f is generic with nodal surplus sigma n, then sigma n is equal to the nodal surplus of the canonical eigenfunction at that point. So it means that whenever I'm looking at the secular manifold, so now to keep you awake, I give you another secular manifold, the secular manifold of this graph with 2 loops and 1 bridge. It's 3-dimensional. It's 2-dimensional in a 3-dimensional torus. This is its secular manifold, and I can color the generic part of the secular manifold according to the values of sigma. And here you can see these colors. And whenever the flow would hit an orange piece, I would get a generic eigenfunction with nodal surplus 0. Whenever I hit a blue piece, I will get a generic eigenfunction with eigenvalue 1, etc., etc. So using this, we now have the machinery in order to prove our theorem. And what we want to do now is show that these level sets have boundary of measure 0, so that we can use the equidistribution. So what we were able to show is that the generic part, sigma g, is open in sigma and has boundary of measure 0. And the nodal surplus function is constant on the connected components of sigma g. So in this case, each colored piece is a connected component of sigma g, and each one of them has boundary of measure 0. So the level sets of sigma also have boundary of measure 0, and therefore I can use the equidistribution. Another thing I'm going to do is, we proved and I'm going to use, is that these are anti-symmetric under the inversion. So whenever I add sigma of minus k, that's equal to beta of minus sigma k. Now, using this, we got our result. Each one of those sets that we want to show that has density can be written as such, using the equation that we showed in the lemma. And this one is exactly those points which lie in a certain, which their k and l lie in a certain set that has boundary of measure 0, and then this thing has density which equal to this measure. So this thing has density, and we prove that we prove the well-posedness. We prove that the nodal surplus distribution exists. Now as for the symmetry, the antisymmetry of sigma show that minus sigma is minus sigma minus 1 of j is sigma minus 1 of beta minus j. So the density of this set, which equal to the measure of this set, is exactly as the measure of this set, because the inversion is measure preserving, and then the density of this set, which gives me exactly my needed symmetry. So let me just mention at this point, because I went through it very quickly and skipping the technical details, but one of the major details, both in this lemma and in this lemma, was using the nodal magnetic relation. So we actually needed to, instead of talking about the nodal surplus, we actually needed to talk about a certain variational problem on the eigenvalue, which was proven to be equal, the Morse index of that variation problem was proven to be equal exactly to the nodal surplus. Using this, we were able to show this lemma and also to show that it is something which is continuous. It's the Morse index of a continuous family of matrices, and then it is something that is locally constant, which proved this theorem. So up to now, I proved the well-posedness. Now, Nir, how much time do I have?
Muted. So you have 10 minutes. Maybe you want to save time for questions and so on. So up to you. Okay, so I will go very briefly on the proof for the tree of cycles, and it's a very insufficient way of showing this proof, just to give you some intuition. So in the case of a tree of cycles, we were able to show that sigma can be decomposed as a sum of local functions. Each one of them is either 0 or 1, and sigma is their sum. Each function only depends on the edge length of a certain cycle. And each one of them is respecting the anti-symmetry. So it means that once we have such a tree of cycle, we can talk about each cycle, whether it gets a 0 or 1, and then sigma is the sum, so it's the number of blue such cycles. And we were able to construct a measure-preserving function on a measure-preserving map on the secular manifold, which we call cat flip. And essentially what it does to this picture is sending this configuration of 1, 0, 0, 1. I'm doing a cat flip at this edge, so I'm flipping everything in this side. So given such a thing, and since I show that such a thing is measure preserving, I can do the following algorithm. Whenever I have some kind of a configuration, I can just flip everything to red, then do a cat flip on this edge, a cat flip on this edge, and a cat flip on this edge. And essentially what I got from all blue to all blue and just one red. I was able to switch only one of them. Using this machinery, I can switch each time one of these cycles, and I can get from any configuration of cycles to any other configuration of cycles, from 0, 1 to 0, 1, with measure-preserving transformations. So it means that each one of these sets of possible values of these indices has the same measure, which means that the sum of how many of them are equal to 1 is going to be beta choose j times this measure. So it's exactly beta choose j 2 to the minus beta. And this gives me the binomial distribution that I needed. And this also shows you that because along the way I only use symmetries which are edge length independent, these are symmetries of the manifold for any choice of L, then my result doesn't depend on L and only depend on the fact that it's incommensurate in order to rationally dependent in order to get the equidistribution. So this is how this proof works. And now just to briefly remind some other things I did in my PhD. So we discussed an analogous problem of counting the points where F tag is 0 and not F is 0. This is called the Neumann count. We were able to address it and to talk about bounds, local properties, Neumann statistics. We had 2 papers on this subject. I also did a work by myself on genericity, proving that generically eigenfunction, the derivatives of eigenfunction doesn't vanish on vertices, something that we needed for the Neumann count. And I've been working on a conjecture on a conjecture that relates to the secular manifold and its algebraic structure, conjecture by Colin de Verdier, which recently I found out that it was solved by Peter Sarnak and Pavel Kurasov. So that's it in start. Now,
as for future work, we were able to address also graphs which are not tree of cycles. Here you see that the cycles can meet at a vertex. We were able to show that such graphs with no loops have also a binomial distribution. And we were able to deal with the families of the following graphs, showing that they don't have a binomial distribution, but at the limits of beta goes to infinity, they do converge to Gaussian, no matter what kind of edge length do you take. So that's it. And thank you for listening, and I'll be happy to get any questions.
Okay, thank you. Any questions? You can just unmute yourself.
I said something.
Yeah.
My name is Uzi Smilansky. First of all, I want to congratulate you, Lior, for what you do. There is a saying in the Talmud which says that you cannot be envious of your son or of your pupil. But it doesn't say that you cannot be envious on the pupil of your pupil. And you are my pupil of my pupil, and I'm envious you for these beautiful results. Thank you.
Thank you very much, Uzi. And thank you for this great conjecture.
But then I have a question which is at the back of my mind for some time, because we speak in general about irrationality. But you know, there are all these Liouville numbers which are irrational, but then they are very, very close to rational. So what happens if you have irrationality of this kind, which is very rare irrationality, that are very well, irrationals which are very well expressed in terms of rationals? This is one question. The other question is a more forward-looking one, and it is the following. When you spoke at the beginning about the way that you described the probability, you always went to capital N goes to infinity. With all the measures that you had, all this, the way that the probability was defined was always in the limit of capital N goes to infinity.
Yeah.
My question is, do you have any idea of how the limit of getting a constant when n capital N goes to infinity is reached? Let us say, is it reached exponentially? Is it reached as a power law? If it is a power law, what is the power? And such questions. Now, I'm asking this question because for the case which you mentioned of integrable problems, when you have Laplacian on a manifold, then one knows how this limit is achieved, is get 1 over capital N in that respect, and the coefficient of 1 over capital N contains a lot of information about the manifold. As a matter of fact, if you know it, you can invert, you can get the manifold out of the spectral count. Is this also a case for quantum graphs?
First of all, thank you for this. Both of these questions are great, and they are actually related, because the rate in which what you're asking is what is the rate in which the flow on the torus would cover this manifold, and the rate of this flow on the torus covers the manifold because it's irrational, and the measure of how much irrational is it can measure how fast it's going to cover it. That is the best I can say. Of course, that's not an answer, and it's something that I would be very interested to try to check if I can say something about it. And I'm happy to say that we have here among the guests Erez Nesharim, which is a good friend and also works exactly on the affine approximations. So that's exactly what you need in order to approximate it. And we actually discussed this a few times, but we didn't get deep into it. I can say that in a certain case, it was mentioned by Pavel Exner in a work on quantum graphs with delta potential, periodic quantum graphs with delta potentials. In this case, where you have the delta potential, you can think about the manifold, the secular manifold is moving. The secular manifold is moving, and it's converging as long as and the flow also moves. And then you have this, you have some kind of a rate. Who wins? Is the conversion of the flow is faster than the conversion of the manifold? And that's exactly where he used certain Diophantine approximations to show that if the graph, the edges of the graph have a certain ratio, which is badly approximating, which is like something which is badly approximated, then you can suddenly get infinitely many gaps in the spectrum. And whether you get infinitely many gaps or not is exactly according to who wins in this race and how fast is this flow going to cover the manifold. So I don't have an answer. I would be very happy to try to give you an answer in the future for that. And I hope Erez here will join me in this quest. Anyone else? Yes,
I have a question. First of all, thank you for the nice talk. Do you have J1 visa?
That's a hard and the שאלה כואבת. No, my interview was rescheduled twice, and my next interview is July 1st, and I really hope that by then things would look better according to everything that Trump is trying to do and the visas. So
good luck.
Thank you.
I have also a question.
Yes, Marina.
You said that you define the canonical eigenfunction by normalization, but then you have it only up to a sign.
I kind of lied. So in fact, first of all, it's up to a ±1 sign. And second of all, also the normalization, I take a normalization according to the amplitudes and not according to an L2 normalization, because I don't want the normalization to depend on the edge length of the graph. So that I can actually talk about the eigenfunction, the real eigenfunction, the Fn of Kn of gamma L, and relate it to the corresponding gamma kappa and F kappa, and they have the same amplitudes. So I just take their vector of amplitudes to be normalized, and then they are equal up to a global sign. So this global sign doesn't change the nodal count, doesn't change the spectral position, doesn't change the nodal surplus, and doesn't change the fact that whether they are generic or not.
Okay, thank you.
But of course, when we talk about eigenfunctions, we always talk about the projective space. We always talk about everything up to a scale.
Thank you, Lior.
Thank you very much.
Okay. Take care.
Bye.
Bye-bye.
Bye.